Hi, this is a supplementary video covering physics, Chapter 18 review, the problems, problems 25 through 29 in review. So there's a number of them. Let's hop right into it. So we'll go right to number 25. And so just real quick, in this chapter, again, we only have one equation. We have Coulombs Law regarding the force from electrical charges, point charges. We have the K, Coulomb's constant, that goes with that in that equation. And then for one of the problems, we have the charge, the fundamental charge on an electron in coulombs. And that was from the back of the book in one of your appendix. So look that up, see where you can find that. So 25, they're saying basically if two charges have a force of 1 Newton between them, okay, I just equated the force equal to the other side of the equation in Coulomb's law. We don't know any of the other variables other than K, the constant here, we would know. Okay, we would know that. But other than that, we don't know anything else. And they said if we triple one of the charges, in other words, up here we just take one of them and we multiply it by 3, okay, what will that do to the forces between the objects? Well, looking at what it does to the equation, if we multiply by 3 in the numerator, it will increase the side of the equation 3 times, okay, which will do the same over here, okay? So our answer is it will increase the force by 3 times. 3 times 1 is 3 newtons, okay? Just kind of more of an analysis type of a problem like they do in our math courses with what they call abstract equations. It's really seeing what happens with no numbers in the equation. Okay, so that's your answer. The net force will be 3 times the original. Now, going on to number 26. They're asking in part A, how many molecules of water in the container, okay? So for part A, they gave us the number of moles was 55.5 moles, okay? And they gave us Avogadro's constant, okay? That there are 6.022 times 10 to 23 particles per mole, and in this case we're wanting molecules, okay? So I'm going to abbreviate that MOL period, okay? And that's molecules per mole, okay? So we see the moles cancel. It's just 55.5 times Avogadro's number. We get 3.34 times 10 to the 25th molecules of water. Okay, part B, they're asking how many electrons then, okay? So they said they took 1 electron from each 100 molecules, okay? So it's going to be that number of moles, okay? What are we going to do? We're going to divide that number of moles. I'm not going to write it out again. We're going to divide it by 100 to get the number of electrons. All effectively it does is it moves the decimal point over. Okay, we now have 3.34 times 10 to the 23 electrons. I'm going to use an E with a minus sign in the superscript in the upper. That's kind of the standard symbol, as you see here, electron with a minus sign. This is the charge on an electron, okay? So that's the number of electrons. Number C, what is that charge on the electrons, okay? So we're going to take that number of electrons and we're simply going to this is the charge on 1 electron, okay? So we're going to multiply this number of electrons times our fundamental charge. 1.602 times 10 to the minus 19th coulombs, okay? And then what does that equate? That gives us 5.35 times 10 to the 4th coulombs, okay? Now to be totally technically accurate. The charge assigned to an electron is negative, so we can go ahead and put a negative sign there because that's actually, fixing my 5, a negative charge. Okay, so that is our answer there. Now, it's not, in some cases, it's not typical to put the positive or negative charge on the charge itself, as we'll see in equations, but sometimes it is. So either way, I won't sweat it there. Mainly, a lot of times we're worried about the magnitude of the charge. Okay, and then, excuse me. So then 26 D, part D was what is the force? Okay, I'm going to put part D over here for problem 26, and we go back up to Coulombs Law. Okay, so we know our constant. They give us the charges. Remember, the constant is in newtons, meters, and coulombs. Okay, so we need our charges to be listed in coulombs, and they are in the book. We need our distance to be in meters. Okay, in this problem, R was 100 meters. Okay, so that's good. The only thing to be careful now, all you have to do is plug all those numbers into the thing there. Make sure, though, you're squaring that 100. When you put that 100 into the equation, okay, put a parenthesis around it and square it. Okay, that's an easy thing to miss. We've all done it a couple times through the course, and that's something easy to miss in the equation. So for that particular problem, the force, part D, ends up being 2.57 times 10 to the 15th newtons. And we notice that is a gob of force. That's a big number of force, and actually, well, it is, because we're taking quite a few. Look at how many electrons we're taking. Okay, a lot of electrons, and we're even though they're 100 meters apart. Okay, that force of all those, I don't even know what that number is. It's well beyond millions and trillions and quadrillions, centillions. It's way up there. You know, if we had that many electrons 100 meters away, we would still have this amazing amount of force between them. So the electrostatic, the magnetic forces are rather strong forces in the universe. Okay, so that's number 26. Now, a lot of these problems, these next ones, I'm not going to do the math or show the substitution. You guys are well versed in that. I'm just going to do the setup and point out a little specialty that might be involved in the problem. Number 27. Okay, we're dealing with Coulombs Law, but what they're wanting to find is the distance between the charges. So we're going to rearrange that equation for distance for R. Okay, so if I do that, if I cross multiply that R squared, well, or say multiply an R squared on this side to get rid of it, take it to the other side, and then divide out the FE on this side. Okay, we rearrange the equation into K times the two charges, and then FE ends up going down in the denominator. And of course, we don't want to solve for R squared, we want to solve for R. So we would take the square root of R, and then we would have to take the square root of this side of the formula. So from that point on, it's just a matter of plugging things in and then take the square root. Okay, so that's, again, so because there's only one equation in this chapter, they're going to do different things, have you solve for different things within the equation. And we've gone through this before, okay? If we're solving for something on this side of the equation, we have to re-express the equation in the terms of that variable or that unknown we're solving for. And that's what we do in 27, okay? So I'm not doing the math. I'll just give you The answer comes out to be 15 meters on that problem. So make sure your numbers come out to that. Problem 27. Okay. Problem 28. We're finding one of the charges now. So we are going to rearrange the equation for the charge. And for my thing, I just picked Q1 as the given charge, and I'm going to solve for Q2. So when I isolate Q2 on the left side of the equation, I divide it out. Okay. Well, I'll leave it over here. It's in the numerator. I'll leave it over here. I'll take everything else to the other side. Okay. So what becomes is the FE on the other side stays in the numerator. Okay. The R squared is in the denominator here. It ends up going into the numerator on the other side. Okay. The K and the Q1 are in the numerator, so when I take them to the other side, they go in to the denominator. So my rearranged equation for Q finding the charge on Q2 is right here. The force times the distance squared divided by the constant divided by the charge on the first one. Okay, and also another thing to be aware of, R, they give us in centimeters, 10.0 centimeters. Okay, we're going to change that to 0.0 or 0.10 meters because we need to have that in meters. So be careful of that in that particular problem. Okay, so when you go ahead and solve that, you plug things in, it should come out to 2.22 times 10 to the minus 7th coulombs. Okay, so get your math to work out on that particular problem. Okay, then lastly, problem 29. They're asking the force between two charges. It's really simple. We're just plugging for part A and B. We're plugging it into Coulomb's equation to get the force between the objects. And again, remember, they give the distance in centimeters, so we have to convert that to meters before plugging that into our equation. Okay, so I'm just going to go ahead and give you the forces for part A, 7.19 newtons. Make sure your math checks out there. Okay, I just don't want you to write down these answers and circle them and call them good. Go ahead and do the equation and show me you're putting it into the equation and solving it. And make sure you can do it on your calculator so that it comes out. Okay, part B, the force was 2.70 newtons. And now they want the combined force in C on sphere B, which is hanging there in between A and B. Okay, so we go back up. Now we recognize, and let me draw this line a little better. We recognize that a force can be represented by a vector. Okay, so what we have here, we have two forces acting on that charged sphere B from two different locations. Okay, so we're going to do vector addition to solve for that. And I'm going to set up a convention here, a reference that identifies these directions as the positive directions, upward and to the right. Okay, so we go back up and revisit A. Now, Coulomb's equation will always give us a positive value because the charges are the absolute value of the charges. Distance is always going to be positive. The constant always going to be positive. So it's going to give us always a positive value. It will not give us the direction of that charge. We have to intuitively, recognize what's going on. Well, in part A, what's going on? Sphere A and B have opposite charges, so that they are going to attract each other. Okay, so the force from part A is going to act which way? Well, sphere A is to the left of B. It's going to act this way. Okay, the force from part A is going to act that way. Okay, now the force from part B, those two spheres are the same charge. Okay, which means they're going to repulse each other. Okay, sphere C is over here to the right. That means it's pushing B to the left as well. The force from part B of our problem is pushing to the left as well. Okay, now we have two vectors. They are in line with each other. Okay, they are not at angle to each other. We don't have to do something like this, a vector addition, to get a resultant. Okay, thank goodness we don't have to do that in this problem. They're both acting to the left. Okay, so the force electrical on B is going to equal the force A from part A plus the force from part B. Okay, what is the force from part A? Okay, 7.19 newtons. In which direction now? Because I'm adding, I need to take account of the direction. It's a negative direction to the left. I'm going to add a force of 2.70 newtons, and again, which way is that? It is to the left, negative. Okay, when I add them together, the force electrical on sphere B equals minus 9.89 newtons. Okay, why negative? Because I've defined it this as the positive directions when I'm adding my vectors together. Now you could do it this way, or you could say 9.89 newtons to the left. Okay, just we have to have that direction. And why do we do that in this case and not the others? Well, because we have multiple forces at one sphere acting, so we have to see what the combined is. In all the other ones, they were just two different charges, and so we either know they're either going to be pushing away or attractive. Okay, but in here, in this case, when we have two different forces involved, what is the net combination of those together? So I hope those help you on your review problems. Shoot an email or a text message with any questions. So long for now.